So next we have Nusha Gailey. There we go. I'll let you do that. Nusha explores the future of cities through the transformative power of technology. She's currently a research associate at the Massachusetts Institute of Technology in the United States and project lead for the Sensible City Lab, sensible with an E, not an I, which is a group dedicated to understanding cities through the advancements of big data analytics, data visualization techniques, and increased computing power. Nusha's work focuses on the creative application of sensor-based technologies in urban systems to generate new data streams promoting resilient, efficient, and intelligent cities. She's also managed the Underworlds project, which is a multi-departmental project that links data that can shape inclusive health strategies and is pushing the boundaries in the field of urban epidemiology. And I think she's going to talk a bit about that today. Nusha's collaborated on work with the UN Climate Change Summit. She's worked with the United States Department of Energy, and she's consulted for the King Abdullah City of Atomic and Renewable Energy as well. In 2015, she was selected by the World Economic Forum as a global shaper, which is a group of leaders under the age of 30 charged with catalyzing change, social change, that is, in their communities. And I think, someone said something about people here being long in the tooth earlier, and no offense was taken, but I'm really pleased to say we do have some people under the age of 30 in the room who are helping us lead us forward. So if you help me welcome Nusha Gailey.
Thank you for that introduction. Just going to make sure these are okay. Good morning, everyone. I'm thrilled to be here today. It's actually my first time in Wales and my first time in Cardiff, of course. So I'm really excited about exploring a little bit later today and tomorrow. So Alison already gave an introduction about me, but I'm an architect by training, actually, so I practiced architecture in the traditional sense for about a couple years before coming back to academia. And so I'm going to start by giving a little background about our lab and maybe actually answer some questions about what academia or universities can do in cities. So our lab was founded in 2005 as a joint venture between the Department of Urban Studies and Planning at MIT and the Media Lab, which is within the School of Architecture and Planning. And the mission of our lab is really to better understand human behavior in cities. We do this by leveraging advancements in sensor-based technologies, so increased computing power, data visualization, and data analytics techniques. And given this broad nature of our mission, researchers come to our lab from many different backgrounds. And I think that this is really key to the success of a lot of our projects. We have people from design and architecture like myself, but then also engineering, computer science, math, physics, as well as the social sciences, just to name a few. So our lab has about 35 to 40 researchers in Cambridge, Massachusetts, with another 10 in our sister lab in Singapore. But Singapore isn't our only international collaboration, and far from it. So our lab operates in a consortium model with industry and civic partners all around the world. Past and present partners include the city of Copenhagen, Qualcomm, Audi, BBVA, the state of Rio, and recently we just formalized a partnership with Uber as well. So these partners are all interested in the same question, investigating how the ubiquity of digital devices and network infrastructures are impacting cities and urban living. So in the early 90s, scholars speculated about the impact of the ongoing digital revolution on the viability of our cities. We saw images like this. And the mainstream view was that because digital media and the internet killed distance, they would also kill cities. George Gilder famously proclaimed that cities are leftover baggage from the industrial era, and concluded that we are headed for the death of cities due to continued growth of personal computing, telecommunications, and distributed production. But in fact, cities have never prospered as much as they have over the past couple of decades. China poured more concrete into buildings, roads, and highways in the past 3 years than the United States did over the course of the entire 20th century. So this digital revolution did not end up killing our cities, but neither did it leave them unaffected. Digital technologies have turned our cities into hubs of data creation, and lots of it. So just to give you an example of how much data we're generating, this is 5 billion gigabytes. And this is the amount of data that was produced since the dawn of humanity to 2003. So every book ever written, the Bible, Shakespeare, every newspaper article, every message, every work of art is within this 5 billion gigabytes of data. And today we're producing the same amount of data in only 24 hours. And this time frame is just getting smaller and smaller. It's getting smaller because we're no longer just producing data from people talking to each other, but our objects are now talking to one another. And as such, our urban environment is talking to itself. So in 2010, it was estimated that we had 5 billion connected devices, or 5 billion connections worldwide. And projections from Ericsson indicate an exponential growth, that we're set to reach 50 billion connections by 2020. As more objects become connected. So as your phone is talking to your wrist, and to your husband's wrist, and to your car, and back to your home. So as this is happening, our cities are really becoming like computers in open air. We like to call it a digital nervous system that's embedding itself over our cities with which we're interacting on a daily basis. So an early example, a project that we did back in 2006, where we set off to visualize a lot of these interactions in the digital realm, was the first time that cell phone data was used spatially to illustrate urban patterns. As you may or may not remember, 2006 was a World Cup year. The final was between Italy and France, where Italy won and Zidane made that infamous headbutt. So yeah, that was 10 years ago. And we used cell phone data to build a heat map of Rome during the game. So with this, we really began to give the public a glimpse into the living pulse of their city. So you can see people are waking up. The red is kind of concentration of phone calls. The time frame is at the top. So around 8 p.m., the city goes quiet. Everybody's watching the game. France scores, Italy scores. Halftime, everyone makes a quick call. Second half, they're tied at this point. End of normal time, very tense. First 15-minute overtime, second 15-minute overtime. Zidane gets the red card, Italy scores, and they win. And the city just goes crazy. So everyone kind of gathers in the northern part of the city, where in this piazza. I don't think they went to bed that early. They were just partying too much, didn't make calls. The next day, everyone gathers, and the team and the mayor actually come down to this piazza to greet all the fans and celebrate with the fans. So this was really the first time that telecom data, so using anonymous aggregated cell phone activity, was used to understand mobility and human dynamics at the scale of the city. And this is just one example of how we can tell the story of the city. So most of the projects in our lab fall pretty neatly into one of these two categories. The first, opportunistic sensing, we're analyzing data sets that are given to us, typically by one of our industry partners, to find hidden patterns. In the second, network sensor deployment, we're actually putting sensors out into the urban fabric, and this is enabled through our civic partnerships to generate data streams that don't currently exist. So I'll just give a couple examples in both categories. So this project, HubCab, was completed actually 2 years ago now, and we take on the New York City taxi fleet. So there's about 14,000 taxis operating in New York City, and these are just yellow cabs, so not Ubers or any rideshare apps. And these cabs are generating a large amount of data on drop-offs, on pickups, and on driving times. So we were interested in what stories this data could tell us. So the Taxi Commission gave us all of the pickup and drop-off locations and the driving times of all the trips over the course of 1 year. So that was 170 million rides. We plotted the pickup in yellow, the drop-off in blue, and we're able to see precisely when, where, and how different parts of the city became stitched together as hubs of mobility. reaffirmed a lot of our intuition in that most of the pickups happen in Manhattan. People are traveling to the outer boroughs. The two airports are major hubs. You can't see JFK in this image, it's cut off. But what we wanted to do with this information was explore potentials for shareability in these rides. So how many of these rides were redundant? How many people were getting picked up around the same location, around the same time, and getting dropped off in a similar location? So we computed the maximum opportunities for sharing, and what we found was pretty astonishing. That if New Yorkers were willing to do two things, one, that was take a small inconvenience in time, and two, actually be willing to share their ride, up to 80% of rides would be shareable. If you increase that inconvenience in time to about 5 minutes, over 90% of the rides were shareable. And we wanted to make this research available to the public so that they could see the impacts of their travel decisions. And this is really something that we do with a lot of our research at the lab, is how can we create visualizations that people can interact with. So understanding that not everyone understands the graphs on the previous page, we created HubCab.org, where people can go on and pick any 2 points within the city. The program computes the sharing benefits if the rides along that route are shared. So I took a screenshot of the website. So let's just take Penn Station and Columbus Circle, two kind of major hubs in the city, as an example. There's over 400,000 pickups and drop-offs between those two locations in a year. Now, if these rides were shared based on our algorithms, they would result, and you can't really see, but it's in the green box in the top left, they would result in sharing benefits of over $3 million spent, almost 1 million miles traveled, and over 400,000 kilograms of CO2 emissions. And this is exactly the kind of research that appeals to our industry partners. So when we published this paper along with the website, we have the academic paper that appears in a leading academic journal, as well as the project was on the front page of the New York Times. We were contacted by Uber, who told us that we've been thinking about a kind of rideshare program or feature on our app, and this was kind of our proof of concept. Not long after Uber rolled out Uber Pool, which I noticed is not available in Cardiff, but you can use it in most cities in the US right now. And then since they've joined our consortium as well. So the next project, Spring Spree, was done in partnership with BBVA, a major Spanish bank. And here we look at financial data. It's some of the most rich and interesting data that we can access. They turned over all of the data on transactions that happened on the point of sales terminals in Spain over the course of 1 year. So regardless of the bank of origin for the card, we had 4 data points for each transaction that happened. That was the location of the sale, the time of the sale, the type of sale, so the category of the business, as well as the nationality of the cardholder. Now, if the cardholder was Spanish, we had their zip code. And we took a small chunk of this data, because again, this was a lot. And we took a small chunk over the course of Easter, Holy Week in Spain, and we plotted spending in 4 different categories. Blue is groceries, yellow is gas, pink is fashion, and red is bars and restaurants. And you can see Monday through Wednesday, we sort of establish a normal curve of spending, or the kind of norm. You can see the major hubs of Madrid and Barcelona. And then on Thursday, we see this kind of spike in bars and restaurants is higher, or highest, from Monday. And then on Friday, we see virtually not too much spending except for bars and restaurants. That spikes even higher as we get closer to the weekend. And on Saturday, we see a huge spike in groceries. People are preparing for the big Sunday Easter meal. Still going out to bars. And then on Sunday, the majority of spending is actually on gas, as people are driving around the country visiting their families. They still go out to the bar. That's a pretty consistent spike. And then on Monday, we kind of reestablish that normal again. So the next phase of this project was to really look at the whole data set and to create an analytical tool for the bank to be able to leverage this transaction data into insights about city spending. So for example, questions we were interested in were, how do different cities attract different types of tourists? And how does that change over time? Can you compare the spending patterns of French nationals in, say, Madrid versus Barcelona? So with all of this, is it working? Let me see. So we created this tool for the bank. Oh, there we go. So we created this series of these tools where the bank could manipulate parameters such as the time range of the purchase, the location, the area of the purchase, and then the category of sale. The nationality of the card users, whether they were domestic or international, and even more, and then the type of sale as well. So a few insights to share with you was that French nationals and Americans, for example, have very similar spending patterns. They spend at the same types of places, so mostly bars and restaurants, in the same parts of the city and about the same times of year as well. And so where French and Americans are very similar, Chinese and Russian nationals are very different. The majority of their spending is on retail and shopping, but in different parts of the city. We found that Chinese nationals tended to frequent the kind of mega malls on the fringes of cities, more in suburban areas, whereas Russian nationals were shopping more in downtown cores and boutiques. So through this lens of spending, we were also actually able to identify a food desert in Barcelona. So for a culture that's so driven by food, what does this mean for the urban fabric? So this tool begins to reveal these new opportunities for business, for the bank. Banks can use this information when lending. It gives them more insight into their customers and gives them more insight into analyzing the risk of lending. So not only creates the power for banks to change their lending habits, but in turn gives them the power to actually change the city. So the projects I just discussed give us some pretty good insights into our cities with data that's already being generated. But what about other information that's currently untapped? So data sets that aren't automatically being generated. As computing power is getting smaller and smaller, we're seeing an emerging suite of miniaturized sensors that we can embed into everything in our urban environments. So where the previous projects looked at existing data sets, the following, we're actually embedding sensors into our cities. So the idea behind this project, Trash Track, was the premise that we know so much about the supply chain, but so little about the removal chain. So take, for example, your laptop. We know where all the various components that make up this machine come from. We know when, where, and how they're assembled, but very little data exists as to what happens when we dispose of this machine. So we decided to find out. So we partnered with Qualcomm here to create thousands of these smart tags, these sensors that functioned essentially like cell phones. They kind of, through cell phone towers, were reporting their location. And then we partnered with the city of Seattle to invite about 500 residents to bring thousands of pieces of trash. We were accepting a whole wide variety of trash, from organic foods to electronics, as well as clothing. And we embedded everything with these sensors and told people to go home and dispose of the items on a specific day as they would normally. So you can see it took about a week for things to reach local landfills around the Seattle area. But then we were really surprised as to how far things started to travel. It took about 2 weeks, things went all the way across the country. And things were traveling for about 2 months as well. So a lot of this specialized e-waste took a couple months to get to its location. So I'm going to pause on this slide for 1 second. So this is the first time that a mapping like this was done. And we can use this knowledge not only to build more efficient and sustainable infrastructures, but also to promote behavioral change. The invisible infrastructures of trash removal are no longer out of sight, out of mind. So we actually allowed people to follow their objects in real time as they were moving through the US. To this point, an interesting story that emerged, a woman contacted us after the experiment, and she was able to follow the journey of her plastic water bottle to a local landfill just kilometers from where she lived. And the thought of that bottle sitting there for hundreds of years for her great-great-grandchildren to have to take care of was so powerful and motivated her to stop using plastic water bottles. Similarly, we can see 2 different routes taken by a printer ink cartridge to Southern California. One travels down the West Coast, whereas the other makes a cross-continental journey through Chicago. And we were wondering why this was happening. And when we looked into it, the one making the cross-continental journey actually had a lower carbon footprint because it was traveling by train, whereas the coastal journey was made by truck. Another interesting thing that we noticed was that a lot of the e-waste, or some of the e-waste, was hitting the coast and disappearing. Because we were tracking them using cell phone towers, they were only trackable within the continental United States. So this really became indicative of illegal e-waste trafficking and prompted kind of a new phase of the study where we wanted to try and follow this trash and see where it was actually ending up. So this last project that I'll talk with you about today is the urban health project that Alison mentioned. And in this project, we're switching gears to kind of look at a different type of trash. Underworlds is a platform to mine human waste for biochemical data. So it's one of the largest projects that our lab has ever taken on. It's a cross-disciplinary endeavor involving multiple labs at MIT. So we're leading the project at Sensible, but we're also working closely with labs in biological engineering, civil and environmental engineering, as well as computer science and artificial intelligence. And what this project, what we aim to do is draw conclusions about the health of our communities. This is often very challenging. People have to self-select as ill, go to the doctors, and once they're there, procedures like drawing blood or taking stool samples are quite invasive. So the premise behind this project is that there is a massive amount of data that's stored in an individual's microbiome. So data on eating habits, genetic tendencies, disease, and just overall health. And you can tell a lot about a person by sampling their gut. So as this data is flushed down the toilet, this vast reservoir of information on human health and behavior goes with it, and it's aggregating in our sewers. And this resource is currently untapped. So we're proposing to develop a human health census by sampling the urban gut, or the city's sewage. So when we think about sewage sampling, or the way that this is traditionally done, is at wastewater treatment plants. That's where the majority of it occurs because everything's naturally aggregating, it's very easy to access, you don't have to go underground in the city, and you also have personnel there who are accustomed to working with that type of hazardous waste. But the problem with these plants is that they're often many miles away from communities, so they're very disconnected, and they collect a lot of runoff along the way. So not only that, but the environment in our sewers is very different from that in our bodies. So by the time the sewage actually gets to the treatment plants, a lot of the pathogens that you might see that thrive in people have actually died off, and a lot of environmental noise becomes abundant. So what we're proposing is to actually sample throughout the sewage network in the city to develop individual readings of particular neighborhoods as well as the aggregate reading of the city. In this way, we're hoping to create a real-time or close to real-time platform that accurately represents defined communities. But this isn't a new concept. I don't know if anyone's familiar with this map, but this was first attempted by Dr. John Snow in a very analog way. So this is a map of Soho in London, where Dr. John Snow was showing the clusters of cholera cases in the 1854 epidemic. So at the time, doctors thought that cholera was an airborne disease, but he didn't believe it, and so he went and took samples from various water sources, so the pump stations in the city, and then mapped them, and mapped the cases of cholera of people whose source was around that pump. And everything kind of converged around one single pump. So he was able to trace the source of that outbreak to the Broad Street pump and really gave birth to the science of modern epidemiology. It was also this that really led to the development of wastewater infrastructure as well, and understanding that we actually need to remove waste from our cities in a careful way. More recently, sewage sampling has prompted emergency immunization, as it did in Israel in 2013, where multiple sewage samples across the country yielded the polio virus. So this was just a group of scientists who were trying to develop protocols to be able to isolate the polio virus, and they were actually able to identify it, and that prompted kind of a wide-scale national emergency to vaccinate all children. And as a result, there wasn't a single case of paralysis. So now, in fact, many countries have undertaken environmental surveillance and sampling projects for poliovirus in particular. So the countries in red do systemic surveillance and reporting to the WHO, and whereas the countries in yellow and blue are doing either ad hoc or research sampling or starting regional priorities. But while the poliovirus provides us with a compelling application, we're interested in so much more. So working together with labs in bioengineering and microbiology, we're designing experiments to look for viruses for the tracking of infectious disease. Currently, disease monitoring is symptomatic, so only when people become sick and they go to the hospitals are we mapping where in the city outbreaks are happening. We're interested in bacteria to quantify a population's antibiotic resistance, as well as chemicals to measure non-communicable diseases such as obesity and diabetes. We can look at biomarkers for those things. But then also, we can begin to measure the downstream effects of public health policy. So for example, when former New York Mayor Bloomberg put a ban on the size of soft drinks that could be sold in Manhattan, can we see 6 months down the line or 8 months down the line a change in consumption patterns or sugar intake in the population, rather than waiting a decade or a half decade to do a survey, which is how it's traditionally done? We can also begin to monitor the use of pharmaceutical drugs, as well as illicit drugs, and see if they correspond with certain times of the year or certain external factors or stressors. So we've designed a multi-step project here where we characterize the sewage network. So we've been working very closely with the cities of Cambridge and Boston in Massachusetts, where we're mapping in GIS the sewage network, so we can accurately say if we take a sample from this manhole, this is the catchment area and the community that we're characterizing. We're collecting and processing these samples and then prepping them for biological analysis. We then want to pair this biochemical data together with urban demographic data to build a front-end platform to visualize and interpret the findings to inform municipal governments, policymakers, health practitioners, designers, urban researchers, and most importantly, citizens. So one of the things that we focused on in this project was how can we actually take these samples out of the ground? Again, we're sampling in the city, so they're in the sewage, and we began to manually collect the samples. That's actually me on the right, and it was not the most pleasant experience. Researchers or PhD students would rather do anything else but this. So in order to get a representative sample, we actually need about 1 liter of sewage to filter. So that was a lot of sewage that we were lugging back to the wet labs. So we decided that figuring out how to automate this process was the most important thing. So we began exploring this question and trying to find ways to onboard a lot of the pre-processing that needs to happen in the wet lab onto a sampling instrument. So this is the second and current prototype that we're using to actually deploy in cities to sample with. And this allows us to pass any given amount of raw sewage through a viral and bacterial filter, concentrating the pathogens while discarding the rest of the sewage. It allows us to experiment with multiple sample sizes while only taking this filter back to the lab for DNA extraction. We've currently built a network of these that we can deploy throughout the city. So they're all controlled via a central decision maker, relaying simple environmental data back to the cloud. So we've currently onboarded these environmental sensors such as pH, temperature, flow, and next we want to be onboarding sensors for targeted pathogens of interest. So just in case you're interested, this is what the sewers look like in Cambridge. So CNN recently made a video of our sampling device, which is called Luigi, from Super Mario Brothers. The first prototype was Mario. So. We have a more sophisticated way of hanging it now, rather than just a 2x4. And the last thing that I'll show with you is, so we're still currently sampling in Boston and Cambridge. We're still in the process of establishing our protocols, both in the field and in the lab, but we're slowly starting to get results back from our sampling. This visualization shows us how the gut bacteria in the sewage changes, in a residential neighborhood changes over the 24-hour course of a day. So we took one sample every hour for 24 hours. And the timeline's on the bottom, and you can see in 1 second, we're going to highlight all the human-derived bacteria versus kind of bacteria that would come out of the environment. So this is all the human-derived bacteria and the non-human. And if we play through the day, so starting at midnight, 1 a.m., 2 a.m., 3, so you can see when it starts to grow. 4. And we see 7 a.m., you see a big spike. People are starting to wake up. They're using the bathroom. Then everyone goes to work. You see another spike around noon. And then what's interesting is that in the evening, you do see a spike as people come home from work, but you also see a greater diversity of bacteria. So you have more people who are home using the bathrooms versus during the day. And so as I wrap up, I just want to highlight these 4 points, that cities will continue to thrive. We must make use of existing urban data that's already being generated and stored, but also deploy our own sensor networks in the city. And finally, we need to design intentional human-digital or human-machine interfaces of how we actually interact with these systems in our cities. And I'm going to leave you with this quote and say thank you.
Okay, I just have to say, my son thinks I draw all day long, and so when I go home and tell him that we were talking about poo today, he's just going to think I'm the greatest mom in the world. I'm really excited. We are very much over time, and I take full responsibility for that, but I think the conversation's great. We're going to go to questions, but I'm going to ask Alistair and Roel to come up to the stage. We're going to bring a couple chairs on stage and have a conversation, and so we can start taking some questions for Nusha and bring Roel and Alistair into the conversation as well.